Please start the session.
Can you ask him? Okay.
Okay.
Okay then, welcome everybody. Today is the lecture 5 where we will be looking into the pre-processing and feature extraction. We will also look into few of the data processing techniques. And these are the main 3 outlines. If you will try to follow the schedule, you can see that today we will be talking about the few of the data processing techniques following what we have discussed yesterday, and some of the terms which we have discussed yesterday. So today is the day when we will talk a little bit about those, and following this one, after that in the next session we will try to solve few of the tutorials, and that's going to be some way the numerical, and then we will also see some of the, I will be using the MATLAB today because that's what I generally use, but if you are comfortable you can actually use the similar kind of things in the Python, and then you can actually kind of do the same thing, okay? And following that, also with the assignment, we will also do some of the home assignments or the homework, whatever you want to say. And I would expect that before the course ends, it's a good idea, or at least before the tutorial 3 starts, if you can send the home assignments to either me or Shamim, then it will be easy for us to also evaluate everything accordingly, right? I will talk about those things in the lecture 6 anyway. So you will see that we were quite talking about the missing data and the missing values, because those are actually important, and they actually, if you will look into this missing data, how they could actually affect the whole performance of this model. You can see that most of the time they quietly degrade the model accuracy. They also degrade the model reliability. So imputation is about replacing the gaps without distorting the signal. So there are 3 missing. So there are 3 missing mechanisms or the method we generally use to get it. So I have tried to kind of list it in the 3 divisions. There are definitely other ones as well, but we are trying to look into the most common ones. We are trying to look into the most evident one or applicable one, especially when we are talking about the civil infrastructure or infrastructure monitoring. The first one is the missing completely at random. We also call this as MCAR. So MCAR is basically missingness which is unrelated to anything in the data. And example can be a respondent accidentally skips a question, right? So that's not going to be affecting the other questions in that perspective. So the impact is generally the list-wise deletion won't bias the estimate, but you lose the power some way, right? And simple imputations are usually fine for this. And then the another one is the Mars missing random, and this is actually being called as a missing random, and in short we say as MAR. So here what happens is that here in the Mars, the missingness relates to the other observed variables, not the missing value itself. So basically then it affects the data compared to the previous one, right? Example can be incoming is missing, but age or occupation are available, and explain the missingness. So the impact is very naive deletion, they can also bias the result, and then we try to use the conditional or multivariate models like regression imputation or those kind of methods that use the observed predictor. And with the MCAR and MAR, there is another one where missing is not random. So the first one is missing is completely random, the second one is missing at random, and the last one is missing is not at random. And in short we call it as MNAR. So what happens in MNAR? MNAR is that where missingness depends on the unseen value itself, okay? Example could be incoming is missing, but is usually or unusually high or low. And the impact can be the hardest case for this particular MNAR situation. And simple imputations, if you try to use simple imputation like MCR, it's not easy. So you need to consider some kind of domain knowledge, you need to consider some kind of sensitivity analysis or explicit models of missingness to identify the MNAR testing. So you can look into that how generally we try to use this or this kind of method is that we try to visualize the pattern like heat maps or missingness matrix. Those are the way we kind of try to do that. We create the missingness indicator for all of this and test the associations with the observed features, and that's how we generally do. And if you also try to use split train or test before the imputation and then fit the imputers on the train model also, then also you can find out some of this. Now you will see that except that we can also explore there are various other imputation methods and if you will try to group or categorize this, they can be mainly categorized in three main approach. One is the unsupervised one is the supervised one, and the third one is the statistical approach. So what happens in the unsupervised method, for each of this method can also be divided into few of the sub methods. So unsupervised method can be divided into two methods. One is mean, median or mode imputation, and another one is the k nearest neighbors. We also call it as KNN imputation. So what happens in mean, median or mode imputation? This is a very fast and simple method, and this replaces the missing numerics with the mean or median depending on what is available, and categorically with the mode. So it's fine with MCAR. And so if you go back here, so we are trying to actually relate with one of this imputation method with this, okay. So if you will try to use the mean and median or mode imputation, this is mainly applicable for MCAR or mildly applicable for MAR, but it shrinks the variance and can weaken the correlation. So that's the disadvantage for mean, median or mode imputation. The another one is the k nearest neighbors, or we call it as an KNN imputation. So for each of the incomplete row, what we do for KNN is that we try to find out k most similar values and that can be happening through the row. So for each of the incomplete row, we try to find out k, that means most similar rows, and borrow their values, and that's what we do here. So that works actually well when local structure matters and the features are correlated. So in that kind of cases, the k neighbor or the KNN neighbor works very well. And the scale feature first, so definitely you have to choose the k via CV, and note that it can struggle with the high dimensionality. So if you have a very high dimensional data and lots of missingness, then it may not kind of work well, okay. So this is mainly the unsupervised imputation, and now if you will look into the another category which is being called as a supervised imputation. So they do also have some kind of divisions or subsets. The main one is the multiple imputation by chained equation, and we do call it as MICA. So what MICA does, it actually builds a conditional model for each of the feature with the missing data, right? And then iteratively inputs it and repeats the whole process to create the multiple completed data sets. So we then pull the results out with properly reflected imputation uncertainty. This is very great for MAR. Again, I will say that we are referring this. It's very great for missing at random and mixed or numerical categorical data, but not for the compute intensive cases, okay. So basically you can choose any of the simplest method that respects your data or your mechanism, and we start with median, mean, you use KNN, or when local structure helps. But if you move to MICE, that means the second one where you need some principles or you have some uncertainty aware imputations. So when you do have some kind of uncertainty in your data, that's the time when you use this one. And when we use this mean, median or k nearest, when the local structure helps, that's the time when you use the unsupervised one, okay. Similar way that you can also explore the statistical imputation method, and for the statistical imputation method you have two types. One is the regression imputation and another one is the probabilistic imputation. And when we do use statistical imputation, when we use it when the simple methods are not enough, that means the previous two does not work out, okay. So what happens in regression imputation, we predict the missing value from the other features like linear or logistic trees. It is very good for MAR when the features are informative. So when you have some informative feature, you can use MAR, and that's the period or the time when you use the regression imputation by using some kind of linear or logistic trees. So the advantage for this kind of regression imputation is that they preserve the relationship, often the lowest error. So you may not find a big difference on the error. But they do also come out with some kind of limitation. So the single regression imputation shrinks variance and they can sometimes overfit. So you have to prefer to embed with MICA or use some kind of cross-validated models, or try to converge your models before you try to use those. and never fit on the full data set. So that's the another suggestion when you try to use the regression imputation. And then there is another one which is the probability imputation, and that also comes under the statistical imputation method. So what we do in the probabilistic, we also call it as a stochastic as well. Please do remember when we say probabilistic or stochastic, we are not talking about the non-probabilistic case here. That means the data set which we are following, we know their distribution. Okay, that's the time when we use the probability imputation or stochastic imputation. So what we do here, we sample from a distribution, like any kind of sample you take. If it's like a random, we generally take the normal or the Gaussian distribution. You can also take log normal, you can also take empirical to fill the gaps. Okay. Then we optionally condition on other features. So first what we do for this is we sample from the distribution we are trying to follow, and then we kind of fill the gaps. Other than that, what we can do is that we can condition on any other features except the distribution. So the advantage is that this maintains the variance and also avoids identical copies of the mean. So that will also help you to get some, or avoid some identical data. But the disadvantage for this one is that you have to choose a very right kind of distribution, because that's where you are actually depending on, right? And you have to add noise, assumption is wrong. So basically you do not add noise for this kind of things, and you have to assume that there is no noise in your data, and that's how you process it further. And you have to also pair it with multiple imputation when possible. You have to do some kind of convergence study, because some way you are saying that distribution, or you are saying, okay fine, your data is following some certain kind of distribution. So it's very, very important that you either converge it or you try to pair with some kind of other multiple imputation method. Okay. And then there are, except these three, that means supervised, unsupervised and statistical imputation method, there are several other ones as well. Another important one which we do quite use a lot for the infrastructure monitoring is the deep learning imputation method. And that's also been divided as an autoencoder imputation. So for this kind of autoencoder imputation is that we kind of use a denoising or the mask autoencoder that learns the data from the nonlinear structure and then reconstruct the missing entities, right? And they are very, very handy for the high dimensional data. When you do have a very big data or very high dimensional data, you can use the deep learning imputation quite a lot. They are very good in capturing complex patterns. They are very good in capturing patterns which are having some multiple features. But again, they have also some kind of limitations as well, that they need the data and compute. Okay, so you can't simply just take some random data or distribution. So you need to have some data, need to have some scale inputs as well. You need to know that what scale you are importing, and you have to also regularize to prevent the overfitting. So overfitting is also another concern when we talk about the deep learning imputation, right? And then there are several other ones like arbitrary value imputation, that's also been called as a centennial value imputation. They replace with the flag 1 like -1 as an unknown category. So something like that. And then you can also see there are several other ones, which is the univariate imputation, bivariate imputation, multivariate imputation, column relationship imputation and categorical imputation. So if you will try to look into all of these categories, you will see that first you have to start with the very simple, that means median or the mode one, and then you can use any kind of complicated one, that means maybe you can use the bivariate imputation. So what generally we do in bivariate imputation is that we exploit a very strong pairwise link, right? And example, you regress y with one of the correlated feature of x, or use the correlation to fill the gap. And that's how we generally do the bivariate imputation. So basically the suggestion is that you start with the most simplest way. That means you start with one of the easiest one, that mean, median or mode imputation, and then according to what you need, you can go ahead with the further complicated one, right? And you can also move into the multivariate as well. So multivariate is again nothing but it uses the several predictors at once. That means it uses some kind of multivariate regression. It can use some kind of random forest imputer. So they are based for the MAR data. Okay. Typically they give the most faithful fits, but they are very cost effective to compute. So you may need some kind of HPCs and all to calculate that. Similar way that also categorical imputation is something very, very important as well. For this kind of methods, we try to use the categorical use of the mode or model based imputers like random forest or so what we do is that we consider adding an unknown level so the model can learn from the missing ones, and that's way we kind of use the categorical imputation. So there are several others as well. So the important factor is that first you try to fit the imputers after the train or the test fleet, and then you kind of include any kind of these methods and try to understand the missing indicator or missing data. But it's also very important to understand the importance of the missing data, that whether they are depending on the data, they are depending on the neighbors of that, and according to that you choose your imputation method, right? And then if you will try to kind of look into the unsupervised imputation method, because we are trying to get into more details into that, because you will see that in the coming, the more if you will spend time onto that, you will see that they are one of the most simplest one. Yet most of these practical cases you may need to use this. So that's why we will try to quickly look into or get into little detail of this unsupervised imputation method. As we said that the first one is the mean imputation. So what happens, as we said in mean imputation, we replace the missing value in a numeric feature with the mean of that feature. Very simple way to do that. And the data can roughly be symmetric. The missingness can be close to MCR. That's the period when we do use it. They are very trivial. They are very fast to calculate that. They are very baseline is like very easy to compare against. So they do have like very fast forward. They are very simple, easy to calculate, very fast. But you have to be careful about some of the factors, like it pulls values towards the center, and it can underestimate the variance as well, and they can also weaken the correlation. So it can also bias some kind of downstream models as well. So you have to avoid if the feature has outliers, or if it's like strongly skewed. So if you have some kind of noise, if you have some kind of outliers, then it's a better idea to, or the better suggestion is to avoid the mean imputation, right? So one of the very good example, as I said, that the filling the missing age with the mean age, right? That can be a good example. And then the next one is the median imputation. So what happens is that the similar idea as the mean imputation, median imputation, but here we use the median. So basically we replace the missing value in a numeric feature with the median of that feature. So the previous one was that we are replacing with the mean, this one we are replacing with the median. Again, it is also very robust. It preserves the central tendency better under skew, but it does have also some kind of limitations. It still reduces the variance. It also ignores the relationship with the other features, and it may be sometimes it possibly happen that if any values are missing, you prefer the model based methods, right? So you can see that first, as we say, that the mean and median has a very similar approach. Most of the cases that you will see that they kind of come across a similar way. But if you have some kind of noise or outliers, that's the time you avoid the first one compared to the second one, right? And you will also see the mean word is quite fast compared to the second one as well. Can we take the questions after this is done, because we have too much to cover, right? We'll take all the questions once we are done, right? So then we will kind of continue with the mode imputation. So the mode imputation is also the similar way that we fill the missing entity with the most frequent category, okay? And when we do that, we do it when low, or medium cardinally features are there. Definitely they are also very trivial, they are very robust, they are very fast baseline. You will find a lot of similarity with the previous two, okay? But then again, it does also have a limitations. It reinforces the majority class and can bias the class balance as well. It's not great when the categories are too many, or they are evenly spread. That's the time when we do not use it. So you have to consider adding an unknown level and missingness flag, so the model can learn that when it is imputed, okay? Then the another important one is that k nearest neighbors, or KNN imputation. This is also another kind of unsupervised imputation method. And for this kind of cases, for each of this incomplete row, we have to find out the most similar row, right? And then borrow their values in the missing row. So mean of for numerics or mode for categorical. So that way we have to do that. So definitely their features are correlated, and similarly it's meaningful. But also they do have a lot of advantages, like you can use local structures for this kind of missing data. You can often, they are better than global mean median mode, right? They do also have some kind of limitations, like they scale features very fast. So you have to be really careful. They choose the K via CV, so computationally they can be really heavier, they can be fragile as well in the high dimension. When you have your dimensionality of the data is quite big, then computationally it could be really high. Or with many missing fields, it can also kind of be really high, because that's the time when it will try to take the data from the nearest values, and then computationally it could be high. So you have to avoid the data leakage for this kind of cases, and you have to fit or train the folds very properly, and also you have to do a lot of convergence study when you are trying to use this method. So if you will try to look into one of the choosing an imputation method is not always one size fits all, right? Think about, there are 4 important factors which you possibly need to think about when you are choosing this imputation method. How much is missing? That's very, very important. The missingness mechanism, that means MCAR, MAR, MNAR, which one actually suits for this? That's very, very important to understand for you. And the data type, that what kind of data you are having, the dimensionality of the data, or the missing data, whether to have that much of data that it could increase your limits of the dimension of data, right? And then the feature relationship. So definitely small missingness, which is like less than 5%, that is quite easy. You have to keep it simple. You use the mean, median, or numerics or mode for categorical for this case, and if it's truly like MCAR and it's like non-critical, then you're dropping a few rows can also be fine. And it happens when your missingness is less than 5%, okay? But when it's large missingness, then you have to move beyond the simple cases, then you have to move beyond the single fields, right? And then you have to use methods like KNN, or you have to use methods like MICE to leverage other features, and then you have to preserve the relationship. So MICE also reflects uncertainty by pooling the multiple imputations. You have to also kind of deal with the uncertainty quantification depending on what exactly or how many data are missing, right? And then as I said that the numerical features, those are also very, very important. Mean for roughly symmetric data we have to use. Median we use for the outlier prone, if there is any outlier or noise we do that. KNN we use when there is a strong correlation with the other predictor, because what we do is that we kind of take and replace the data with the neighbor one. So you have to be very, very careful. There has to have some strong correlation with the data, right? Otherwise you cannot use KNN. And then definitely, as I said that these are the 4 important parts which you need to be aware of, and you have to use the simplest method depending on that. So definitely not always you can do that, but your target has to be using the simplest method that does not violate your data assumptions. So you must have also taken some kind of assumption and also escalate to model based methods as missing is the structure, right? And then if you will, noise is very, very important. Noise also kind of bring a lot of uncertainty, and they are very important when we talk about infrastructure monitoring. So we need to kind of understand how do we reduce the noise. So the noise reduction is very, very important, and we can do this in several ways. There are several kind of methods we do use it. So smoothing is actually one of those. So smoothing helps to filter the high frequency noise. So we can see that there are like lot of underlying trend, and then where we can use this kind of smoothing method. So what we do is that in the smoothing method is that we take the last endpoint. So if you will try to look into this particular equation here, this is the equation where we try to talk about moving average, and this process is mainly the smoothing method. So what we generally do is that if you will look into this equation here, the last n is this one that observes the each gate weight, that means like 1 by n. So example, if you think about, so let's first look into this graph here, then we will come back to the equation. So if you will try to kind of look into this chart, this is actually comparing how moving average and exponential smoothing can weight the past, okay? So the black dashed line, if this one you can see here, the line is a 5-point moving average, okay? And the last 5 observation each get equal to 0.2, and anything older than that can get 0. So you can see that after that anything is coming as 0, right? So the colored lines, if you see the other ones like the yellow, red and the orange one, the colored lines are generally exponential smoothing with the different alpha values, okay? So if you will see this kind of moving average, you can see that you want a hard and fixed window, a window with equal emphasizes. We use the exponential smoothing when you want to use the data. So now if you kind of come back to the equation again, And let's try to see that what this equation is actually mean here. So as I said that noise reduction is very, very important, and we use the smoothing. It's one of the process of reducing the noise, and what it does is that it helps to filter the high frequency noise. So when you have some high frequency noise, you try to use it because we can see the underlying 10, okay? So now if you will try to look into this particular equation, we take the last n points and replace the current value with their average. That's what we do here in this process, okay? And how do we do that? We do it with this equation where MAT equal to 1 by n summation of I to n xi minus I, okay? So what is MA? MA is the moving average, and it smooths over a time t. So t is a time here by averaging fixed number n, okay, for the past observations. So basically, if you will see that the last n points are given equal to 8, and the older data outside the window are discarded. That's the reason if you will see this particular graph here, the black one, this all became 0, right? And then when the weight is assigned to each of the n observation is 1 by n. So this is generally the equation by which we try to kind of use the smoothing pattern. And then you will see that there are a lot of other, other equations and other derivations are also kind of associated with that, which we are not looking into that because it's a big derivation. But this is very important for you to understand two things. The first is that this equation and understand this equation. Another important thing is that older the data points outside the window, they are always become 0. That's one of the very important point to look into this graph and understand that when we kind of try to use the smoothing method, okay? So basically smoothing method is that when you want a hard fixed window with equal length sizes, and we use, as I said, we use some kind of exponential smoothing point. And so basically if you will try to kind of look into the example here, as I said, in a 5-period moving average, each of the last 5 observations, this is the weight of 0.2, while older observation is 0, because we said that the older observations we are always discarding for this case, okay? And then if you will go back here, so that's how we generally plot it, weight versus age, because we are taking as a weight of past observation in the moving average and the exponential smoothing. So generally that's how we generally try to put it that. We will try to see some of the, I think 1 or 2, I will say that, not MATLAB, like 1 or 2 equations today in the tutorial to kind of understand it a little better. And then you will see that this is the equation, how do we use it. So in the MATLAB, they do have a direct, or in the math work, they do have a direct, simplifier of this. When you select that, you can automatically get it. So you don't need to always implement that. We will see those things today. Then another important one, if you see this one here, we are talking about the noise reduction method, right? So another important one is the exponential smoothing. This is also like prioritizing the recent data. And that is also something we kind of mathematically, if you can see it here, we can mathematically represent something like this, okay? So if you will see this equation, so each of these new smoothen value is a blend of the last observation. So it totally depends on the last observation and the previous smooth. These are the two important factors which is important for this kind of cases. And this gives a geometrically decaying weights on the past, okay? So no hard cutoff like a moving average. That is compared to this one, okay? So this one basically depends on two things. First is the latest observation and second is the previous mode. These are the two things we need to be careful about. And why do we use that? More recent data, when counts more, older data never fully disappears, right? So if you will try to kind of see this value of alpha, that's one of the important factor for the exponential smoothing, and they actually determine how quickly the older observation lose the influence. This is the factor which is deciding that what are the data you need to consider when you're when you are considering the influence of this, and that can change. So we will look into this. So depending on the value of alpha, right? So the alpha can be, if you see the different value of alpha here, let's take it as a color line, right? If alpha can be 0.3, that means that we get big weight on the newest point, that means very, very responsive and less smooth. If your alpha value can be 0.2 and we are taking it as an orange line, so basically we are trying to talk about this, okay? We are taking this reference but in a different perspective. I didn't show the graph here. And then the similar way, if we choose the alpha by the validation, like if you choose it using MAE or some other way, you can actually get the value of different alpha and then you put it here, and then from that you can get a graph, okay? And the graph will be for different cases of alpha. So alpha can be value of 0.3, 0.2, 0.1, and that will let you know that the value, whether weight decays more gradually whether weight decline very, very slowly, whether it decays very, very quickly. So from the graph, you can understand that. Basically, what you need to do is that you have to pick an alpha to trade the smoothness or responsiveness. So so picking an alpha is some way that's important. Higher the alpha, first changing the signal. Okay. So lower the alpha, then you will want a very steadier trend. So choosing the alpha is very, very important for this kind of exponential smoothing case, right? And then now if you will look into the other one, so you will see that this one is something we also kind of use the categorical data. So categorical data is that variable that describes the groups, that describes the levels, not the magnitude. Most of the ML models need the number, so we must encode these categories, right? So there are two types. Generally, we try to kind of define it. No natural order, like when we talk about the no natural order, it means like example of city. That means we are not saying okay, Delhi, Kolkata, Banaras, Bangalore, not numbering that, right? Or we can talk about the product type, like animal, different kind of product in that way. So we encode with one hot or dummy encoding, or we don't pretend there is an order, right? So what is exactly the ordeal data? So the ordeal data has a meaningful order. Example, that education level, like high school, then diploma, then you do your bachelor's, master's, PhD, or rating like bad, good, best, excellent, something like that. So the ordeal will always have a meaningful order, okay? Whereas when you talk about the nominal data, they do not have any kind of natural order. So they kind of talk about different products. They kind of talk about like different cities, different animals, something like that, okay? And then you can see that that's how we were trying to actually differentiate it. So where you can see the nominal, we are talking about different products here, like different books, pen and all of that, or different study materials, you can say, different animals, you can say. Whereas in the ordeal, we try to show the different emotions, and then it's like happy to sad, right? And similar way. So that's basically you do have some kind of order. This does not have any order. As simple as that, right? And now the two common ways to encode the categorical feature, as I said, one is the hot and one is the level encoding, right? So this slide, if you look into that, we are talking about the one hot encoding. So as we said that the one hot encoding is one of the best nominal variable. Again, if you look into that, the nominal is basically, we do not have any natural order, okay? So that's the period when we use the one hot coding. Basically what we do is that we create one binary column like this, okay? Per category, and put a number 1 in the column that matches with the row category. So you can see that we have created a column like this, right? And then we have created something like this. So when the red will come, we will put 1 here and 0 for the other one. Similar way we have done for green for this one, right? And that's how we do that, okay? So this avoids giving a category as a fake ranking, right? And why we do that? We do it because it works well with the linear models, it works well with the trees, it works well with the neural trees. So that's the period when we do that. So it keeps distance the meaningful because of the category and don't get any arbitrary number. But they do also have some kind of limitations. They are high cardinality, exploit the number of columns and memory. They also consider groupings very rare levels. And the frequency and targets of the encoding or hashing, they can be very, if there are many categories, then it can also be complicated, right? So we have to ensure that the train or test have the same column. That means when we are talking about red, it should only mark red, not the other one. When we are talking about blue, it should only mark blue, not the other one, right? That's the thing you have to be very, very careful about. And then definitely, as I said, the result is sparse. So you have to use some kind of sparse matrices if possible to analyze that. So this kind of one hot encoding is fit the encoder on the training data. It can save the mapping. It can also apply consistently to validation or test, right? Another continuation of that, as I said, the advantages that two of the very good advantages is preserve the information, that's compatibility, that's very, very good for that. And then the user cases. So there are like 3 user cases which you can see. The first one is the nominal data. That means when the category have no order, as I said, the animal type, product type, and across the ML model. It can also be used as an across the ML model. That means if a category is absent, okay? If a category is absent, then you can also use this one hot coding. That means you can use one hot vector is all zeros, okay? And we can add the separate unknowns in the column, so models can learn from the missingness, and we use some kind of imputation method to calculate the missingness, and that's how we generally do that. And then also another important is that, as I said, the handling the missing values. So you can actually use this one-hot coding for the missing values as well. Then the another important one is the label encoding. So what we do in the label encoding is that we convert each category into the integer ID. That means red we are integrating with 0, green we are integrating with 1, blue we are integrating with 2, right? So in the previous one what we were doing, we were making a column. For each of these we are integrating only with 1, others with 0. That means each time there will be something on red, this one will become 1. Whereas for this one, we only have one column, right? And each of this column we are numbering the different cases, right? That's how it, and what is the time when we generally use this one? So we use it for the ordinal features like with a real order, like when you have, you know, small, medium, large, those kind of cases, or when you actually kind of, if you go back here, for this kind of cases we generally use that, okay? And for the nominal one we use the one-hot getter. So basically, when you know that you have the feature, when you know that like sizes, your education, many kind of those emotions, anything you can use this time. And when you know the order basically, that's the period when we try to use the level encoding, okay. It preserves that order so the models can learn from monotonic, monotonic relationships. But it also does have some kind of disadvantages. It preserves, you don't use it for nominal data like color. So if it gives like red equal to 0 and blue is 2, that implies like some kind of fake distance, and that can also bias the linear models like GIAN, SVM. So for those kind of GIAN and SVM, we don't try to use this one. So these are actually very good when you have some ordinal cases, and if you have some explicitly set the order in the encoder. That's the period also we do use it. This also fits the mapping on the trained data. And if the feature is nominal, as I said, or highly, if you know all the orders, then this is the best time when you use this kind of methods. So the main takeaway of this label or some way you can say the ordinal encoding is that they only good when the order matters. When the order matters, that's the period when we try to use this label encoding, right? Otherwise, choose the hot one because that's the easiest one compared to this, right? And then continuing the label encoding because that's how it works. So similar way, if you look into this one, this particular figure, and how it generally works, you have to pick the categorical feature to encode, right? You want to pick anything like you assign any unique integer to each of this category, like ideally following the true order if it's not ordinal, and then replace the original label with those integers and reuse the same mapping for like any kind of test data. As I said that it is very good when you use the ordinal cases, so ordinal variables with some kind of meaningful ranking like education level or any kind of label, it is very good. For tree based model it is good. So when you have some decision tree, when you have some random forest, when you have some boosting, so those kind of tree cases it can actually handle very good. When you have some label encoded features because of the fact that it can split the data very well on thresholds rather than the distances. But you have to avoid this kind of models, or you have to avoid the label encoding when there is encoding for nominal. That means that the order is not in the place. You have some unordered features in linear or SVM, those kind of cases, or any kind of distance based method or distance based model. You better not use the label encoding, okay, because it can create some fake hierarchy. Then you use the other one, which is the one hot method, okay. So for this one, it is very important that you divide the unseen categories, or you map the unseen categories and then log the mapping on the reproducibility. So in order to understand that whether you are using this label one or you are going to use the one hot one, the main important factor is to understand what kind of data you are having or what kind of missing data you are having, whether you do have some kind of category being mentioned. If your category is not mentioned, whether it is having some kind of decision tree, random tree based method, or you have some unordered method, or you have kind of dealing with SVM, or you are using some kind of machine learning like linear regression or distance based model. That's the period you have to decide whether you want to go ahead with the one hot labeling or you have to use the label encoding method, right? So now if you will see that there are also the way we can change the sample we train on, okay. So the idea is to like understanding that the random sampling can be done in several ways. Definitely we are talking here about oversampling and undersampling, but it can also be mixing of this oversampling and undersampling as well. So oversampling, what we do is that in oversampling also there are two types. One is the random oversampling and another one is the synthetic oversampling. So in the random oversampling, we do is like we duplicate the minority samples, like simple but they can overfit, okay. And in the synthetic oversampling, we do is that we create the new plausible points, that means like bordering smooth or something like that, and use the data augmentation for images or time series. It keeps all the majority data but must be done inside the training fold to avoid the leakage, okay. This is the two ways we do the oversampling, random and synthetic. Similar way undersampling can also done in the similar two ways. One is the random undersampling and another one is the informed undersampling. So what we do in the random undersampling is that we drop the majority of the sample. This is very fast because we are dropping a lot of samples here. They are very useful when you have tons of majority data. So that's the period we do not care even if you are dropping some kind of majority samples. And what is informed undersampling? They remove the ambiguous or overlapping points. That means you can use some kind, you use the nearest k neighbor and you edit that and to clean the decision boundary basically. The main risk of this kind of informed undersampling is that you can lose some kind of information, right? And you can underfit if the data is not scarce. So these are the main two methods like oversampling and undersampling. But as I said that there could be some time when you can use both of these together also. So both the oversampling and undersampling can also be kind of used together to understand that depending on the need of the data or the type of the data, you can use it. But you have to pick either oversampling or undersampling depending on the small data sets. If you have small data sets, you can prefer the oversampling. If you have the huge data sets, then undersampling can spread the training, right? So basically, if you have small data, use the oversampling. If you have, and then again oversampling, if you have not worried about overfit, if you can duplicate the minority, but if you are very concerned about the point, then you can use the synthetic oversampling. Similar way, if you have large data, but if you have like a lot of information, like tons of majority data, then you can use random undersampling. But when you don't have that, but you still have a large data, then you can use the informed undersampling. So this is the way generally depending on the number of data, we use the oversampling and undersampling. Then another important part is that the synthetic data generation, okay. So basically the synthetic data, they are artificially records or mimics the structure and statics of the real data, right? But they do not correspond to the real people or real event. So we create them algorithmically, so to stand in for the real data, when it's scarce, it's sensitive, it can be costly or risky to collect. That's the period we kind of try to mimic the structure and static the real data. So it actually enables the software to test and ML prototyping without exposing to the PI. And then it also helps to the rare events and class imbalance. It also helps when it's very risky to collect that. It's not possible to again do the testings and all. It also speeds up the experiments when access to the production data is restricted. So that's the period when it is extremely useful. So there are generally three types of the ways we generally do that. The first one is the structured one, which is mainly like tabular, when your data is based like rows on columns. That's the period is called as structured one. When you have unstructured data, that means you have images, you have text and audios, and then you have the sequential data. That means you have time series or event streams. That's the three types of families we generally do use it. So if you kind of think about the first one, so now what we will do is that we will try to look into each of these in detail, right? What is the structured one? The structured one is that if you think like a customer tables or credit risk record or critical register. So basically how it works is that you do have a database, like you do have like a column or you have a row, and you generally kind of take it from there. So basically we use the encode constraint for this, like or class balance very explicitly when we try to do with the structured data. What we do is that you generate some kind of train set statistics, like you try to avoid the leakage, and you version generator, and you use some kind of random seeds and label your synthetic data and try to connect it with the real experiments, and then understand that how converging your data is. And then the structured data, as I said, that you generate some artificial tables, that preserve the distribution and relationship of the data set. That means means, variance, correlations. So those are the way that we try to do that, but do not reference the real individuals. You have to understand that you are mimicking the data, but you do also have to understand that they are not the real ones. You have to do a lot of convergence. You have to look into the, if you think about the customer records, like the profile, demographic or purchase history, those are the ones which we always refer. Then sensor reading is something like simulated to IoT or industrial signals with realistic ranges or error patterns. That's another thing. So basically how it's being generated, it can be generated using statistical models, like you can use Gaussian couples, copulas, you can use Bayesian network to sample new rows that can match the joint distribution, right? So that's how also you can create that. So generally we try to evaluate the utility for this kind of case, and then we can do the testing of the privacy risk. That means uniqueness of that data, the membership tests of the data. So that's how we kind of do that. And how do we do that? We build the generator from the training fleet only to avoid any kind of leakage, to avoid any kind of outliers. And then we do the version of the model plus seed of the reproducibility. So that's how we generally do. So you can see the structures data. Structured data is something more we generally consider in day-to-day base, but sometimes it's not very practical. But the structured synthetic data help us to prototype, share and balance the data set safely while retaining the statistical signal model. So we are basically using some kind of statistical model to generate this kind of data. So some way we are also relevant. But one thing we have to also understand that there can be some kind of uncertainty, there can be also not many relevance with the real life data. So that's the reason we kind of need to lot of like fitting and convergence study when we are talking about structured synthetic data. And then there is another two types of this synthetic data generation. I think one of the complicated ones compared to the structured data. One is the unstructured data and another one is the sequential data, right? So unstructured data is nothing but when these have no fixed table schemes. That means for structured data, you have a tabular format. You have your row, you have your column, and you can actually do that, right? Where when we talk about the unstructured data, you don't have any fixed table scheme, like you talk about images, you talk about audio, you talk about video. Those cannot be generated making a tabular format, right? You cannot put it as an column or row. So that's the period we kind of use the unstructured data, synthetic data, because we use the generative model to create them, okay? So if you think about image, if you have some image, then we use the diffusion or GIAN tools like some kind of stable diffusion tools for data augmentation and then rare edge cases, right? If you have some kind of audio data, then we use generally some kind of music generator or there are like ETS to create the accent or noise condition if you don't have. I mean, that's what we quite do in the music failure. And then text, that's also one kind of unstructured data which you cannot put as a tabular format. So that we can use LLMs or there are a lot of other ways like Claude or Mixtral, many methods are there, and we use those to kind of produce the label sentences, and we try to understand the summaries or advisal examples. And then if you have videos, then definitely we use GenAI. GenAI is quite very much using nowadays to simulate the scenarios that are hard or unsafe to film, right? Some of the cases like you kind of use it, do it using GenAI. So when you kind of try to use the unstructured data, you have to control the contents with the prompt or conditioning. You have to be very careful about that, because at the way you are mimicking it, they may have some kind of difference with the real life scenario. You have to be very considerate about that. You have to check the bias, right? You have to check the copyright or safety policies as well. You have to also check the distribution shift as well. And then the quality insurance, like you are using audio, you are using some kind of human review for text. So you have to be very careful about using the data, okay? And so this is basically the unstructured data, so which cannot be labeled as the column or the rows, that means not a tabular format. And then there is another important one, except the structured or the unstructured data, and that's been called as a sequential data. So what is sequential data? Here is that the order and timing matters, okay? That means like time series, event logs, sensor streams. So those are the kind of examples when we do use the sequential synthetic data. So basically if you think about the time series here, so synthesize the stocks or the energy or the weather pattern while preserving the trend. You have to preserve the seasonality as well, right? And there are a lot of kind of methods we do use it for that, like diffusion for TAs. There are LSTM. There are many methods we kind of use it. Then there is another way, that event log. So like we have to simulate user journey or failure cascades. There are HMM or Markov chain. So those are the ways where you kind of try to use an agent-based simulator to understand that. And then another one is the sensors, which you do use in the infrastructure also. So what we do is that if we do kind of want to create that, we generate continuous stream with realistic noise. We also kind of try to outage and useful of anomaly injection and stress testing, right? Those are the things we do. They are very good sequential data across both, like think about encode constraints, like when you think about the range, when you think about the time steps, when you have to kind of balance the level, they are really good. They can generate from 10 only to avoid any kind of leakage compared to the unstructured data. And they kind of level the provenance, that means real versus synthetic. They can actually give you some kind of information into that. You can also validate them by train on synthetic or test on real performance, basically. So you can actually compare that with the convergence study with the real life experiments, right? So basically unstructured and sequential data that let us create some safe uncontrollable examples and rare events, definitely boosting the robustness where real data are limited or sensitive, right? So now if you try to look into the structured, unstructured or sequential data, so which one do you think is most trustworthy if you kind of thinking about synthetic data generation compared to the other two? So when we are talking about synthetic data, that means we are mimicking or generating new data which may or may not have some kind of relevance with the practical data, right? So there we have structured, unstructured as well as sequential data. So now if you as an engineer, if you don't have some, if you may have some missing data, so I am not saying that can be image, I am not saying that it can be column wise. So which one you think is most trustworthy if you try to mimic it using any one of these methods? Anyone? Structure?
Because we can use SMT or different kind of techniques to get synthetic data. Whereas for unstructured and sequential data, it will be more computation intensive or more complex to get synthetic data.
But if you do not have, if you get something as an image, if you get something as a text format, then you cannot do that. And why you do not want to use the sequential one? The sequential one may give you better assumption compared to the unstructured data. Anybody? Anyone? Yeah.
Process the data according to the logs, time series, or when it is
Yeah.
generated.
Yeah.
And if we talk about unstructured data, here we are directly using the generated images or
Yes.
generated data.
Yeah.
So it would help us to determine the actual set, whether it is synthetic or real, or then it will be processed according to that data for further results.
So if you compare with the unstructured one with the sequential one, so which one you think is more practical, especially when you are trying to mimic it or get some synthetic data compared to the practical one?
Non-sequential,
Yeah.
because when we reverse track the image,
Yeah.
the time log and data can also help us in preventing
Yeah.
that synthetic data.
And they do also have some kind of information from the real data.
Yeah.
Compared to the unstructured one, because unstructured one is like you are actually generating all of this using some kind of AI models, right? Yeah, correct. Anyone else? Why I cannot hear you? I cannot hear you, sorry. Yeah, but when we think about infrastructure monitoring or any kind of monitoring, right? So our aim is also because we are some way using the AI models, right? And when we are kind of trying to generate fake data, not fake data, maybe synthesized data. So our aim is definitely to understand whether it's computationally efficient or not, but also to understand the data which we have generated, whether they have some kind of relevance with the real one and all, right? Because if you do have a lot of images and all, your unstructured one can also be computationally heavy. Okay, compared to this one, definitely it is not heavy. But if you think about the unstructured data, we do create everything using AI, right? So the relevance with that, with the real one, isn't it like less compared to the sequential one? Yeah, noise can always be removed later, right? When you are using the ML models, and then you can always some way outperform the outlier, some way that, right? Can't you do that? Yeah, but then also when we are thinking about the monitoring or getting the data, don't we want some data which have some practical relevance? That's the reason that it will kind of be more practically relevant, or it will have some kind of real life relevance compared to the other.
In case of computational intensiveness, in unstructured data also to train generative and adversarial intelligence, we need high
So unstructured, structured, all of this they depend on what kind of data you use. So all of this depending on the data set. If it's like small, then definitely it's not quite expensive. But if you compare it with the big data sets, then it can always be. But we are also remembering here, we are trying to talk about HPC, we are trying to talk about ML models. So we are not quite worried about the computational efficiency. And we are talking about sampling techniques. So basically, if we need, we can also select a less number of samples to kind of replace that. But our aim somewhere is to get the data which will have some kind of relevance with the real life, isn't it? So if you see among these three, only the sequential data will have some kind of history compared to the other two. So definitely it depends on what we need. Sometimes we need the unstructured data because that's going to give us a very quick method to do that, and sometimes we are not quite worried because we do have a lot of information. Like maybe we do have a lot of information of the dog, right? How it could possibly look like. We have a lot of images, we put it that, we exactly know that, okay, fine, with this many images, we can actually identify what is dog, what is cat, right? But sometimes we do not have that kind of information for a video, sometimes we maybe didn't shoot it, we do not have it. So then we ask the AI to make that one. So that's the time when you may not know that whether the person actually reacted in the same way, whether the things actually reacted in the same way. So that's the period when things become little crazy, right? And that's the period when we kind of lose the relevance with the real life as well as the synthetic data. So I think it depends on the situations, it depends on the knowledge you have, it depends on the data you have, and according to that we generally kind of choose this 3-1. But yeah, I think among all of this, sequential data is the one which will have some kind of history back with the real data, and that's the reason if you kind of comparing among these three, then definitely sequential data does kind of bring some realness compared to the other two. Are you all with me? Right?
Still, I think it's still user specific because as we said,
Yeah.
we go on user specific.
Okay, because at the end of the day,
For monitoring, definitely you need it
yeah.
because you want access it. But randomly, as you said, if it is a picture of a dog or cat or something, then you don't really need sequential data for that.
Yeah, so for that we are not talking about sequential data. When we are saying that the unstructured data, when you do have a lot of information, right? You know that, okay, fine, you do have a lot of information how a dog could look like, then you use the unstructured data, right, or unstructured data evaluation, right? That's the very easiest way. But when you kind of want to get something which do have some practical relevance or the real life relevance, like the video what I was saying, then sometimes you may need more information to kind of really understand that whether the creator is actually going to react the same way which they are reacting on the previous or the last, and what actually happened in between. That's why you will see that there are like a lot of crime scenes when the police try to investigate. They think about a lot of options that how they could actually things could happen. But you Sometimes you will also see that most of this does not have the, maybe sometimes not true, right? So that can be little tricky. So that also depends on the user, that how trained the user is and how trained they are, using that models.
Like now the video generators are available in AI.
Yeah, Gen AI and all of those.
So
Yeah.
in first case, when video generation was technique was evolved, it was mostly thought in reference to unstructured data, and in that case the models were hallucinating a lot.
Yeah.
We see many unreliable features like 6 fingers in one hand or 12 fingers. Those things were hallucinating. Hallucinations were present, but when included the sequential data, like previous frames of a video, then that video generation model efficiency was much more improved. So from that example, we can also see that sequential data is superior.
That's absolutely the case, but when you kind of have the enough information, like when you kind of say, okay fine, this is how actually it could look like. I'm not talking about the video. Video is definitely, you need some kind of lot of information to put it. But when you talk about generating the image, if you kind of write a comment very, very carefully, that this is something I want, then sometimes if it's the easier one, then I think unstructured data is not too bad. Like when you are talking about simplest image creation or, simplest, maybe including some kind of noise or some kind of video generator, those are okay. But when you are, creating videos or trying to understand what is there missing, absolutely that there are many information you need to feed on to understand how the creature actually behaved or what actually could possibly happen, right? So yeah, I think it's always like a discussion or the debate, but it's like always for the user to kind of how knowledgeable the person is and what kind of inputs they are giving, what kind of comments you are giving. If you do not give proper comments and do not even understand, then always you still kind of get a lot of errors, right? And then comes with this another important factor, which is called as a principal component analysis, and this is we shortly call as a PCA. So you will see that PCA is also one of the very, very important factor, because the principal component analysis actually takes many possible correlated features and they turns them into a small set of uncorrelated components, and they can keep most of the variance, okay? And then that gives us a compact information rich representation, and that's where the PCA is very, very important. It also helps in machine learning model, generating machine learning model, analytically doing that. And how they do that? Firstly, one of the very important factor is that with the big dimensionality. So this actually helps to reduce the dimensionality, right? And like simpler models or less overfitting models or faster training. So they kind of tackle the dimensionality very, very well. And then another important thing they do is that decorrelation. That means they remove the multicollinearity, they stabilize the regression models, and they feature the weights. That's another important factor. And another important factor what it helps to ML model to analyze is that they kind of use the denoising or the compression. Okay, so they reconstruct with the top of PCAs to filter the noise, to filter the any kind of noise in there and shrink the data size basically. And they are quite very useful in the SHM, because the sensor fusion and compression is one of the very, very good example where PCA is being used. They combine many accelerometer or strain gauges into a handful of PCs for real-time monitoring, right? That's where we kind of use this kind of PCAs quite a lot. They kind of also use in damage and anomaly detection, like you can train a PCA on healthy data and monitor the scores. So and then also you can residuals, like you can read the thresholds, you can understand when the signal is not normal. Those kind of cases you can also identify that there are some kind of anomaly in your noise or in your signal. And then another important factor which PCA or principal component analysis does is that they kind of use the mode or feature extraction. So basically, if you think about the PC loadings, they can often align with the model analysis, right? So they are helpful for pattern recognition. With the PCA, you can actually use the pattern recognition. You can use also the image processing. You can use the signal processing like vibration spectra and those things. So you can use those kind of things quite a lot. So if you can try to standardize them and standardize the input, you can also kind of use the PCA quite well. Basically, PCA gives the SHM a compact, decorrelated, often very denoised as well, feature space that improves the modeling, that monitors the health better, and also early anomaly detection. Those are the places where PCA is quite useful when you think about the SHM application. Now, if you will try to quickly compare it with the PCA, with the with the other methods or the applications of PCA and SHM, and try to understand why this is important. So, PCA is an unsupervised dimensional reduction. Okay, mainly when we say about PCA, it's basically an unsupervised dimensional reduction method. It finds orthogonal directions of the maximum variance and builds a new variables, right? And that's we call as also a principal component. So no labels are required or no labels are needed when we talk about PCA. Where what is LDA? LDA is a supervised method. It chooses the direction. So you have to understand these are all kind of talking about dimensional reduction, making your model quite easy. So yeah, what LDA does is that LDA is also linear discriminant analysis. Yeah. Okay. So what LDA does is that compared to PCA is that it chooses distinction direction that separates the known classes, that means the maximize between the class variance or minimize within the class variance. That's what they do. So we do this kind of linear discriminant analysis when you have level states, right? When you don't have the level state, that's the period when you use the PCA. That means when you know whether it's healthy, whether you know whether it's damaged, that you level these things. That's the time when you use the LDA, and you want the base low dimensional separation, right? That's the time when we do it. And then the factor analysis is also another latest development, and that's the latest variable model. It explains the covariance quite well. Then if you try to compare the PCA with k-means clustering, so again PCA reduces the features, right? Where k-mean group k-mean group samples the different goals, they definitely work well together. So if you use PCA first to denoise or and keep saying okay 90 to 95% variance is there, and then you run the k-means, is that a compact space for more stable cluster? So most of the cases you will see that instead of comparing whether PCA is good or k-means are good, people try to use it sometimes together to get better performance, to get more stable cluster. And then if you kind of try to think about PCA, they also most of the cases you will see that you have to reduce to a few PCs, right? That means depending on sometimes 20 to 20, 2 to 20 depending on the signal richness or whatever, and then tune the number of the cluster with the k sequence. So basically what we do with the PCAs and k-means is that try to use it together to get the stable performances. Whereas for PCA and LDA what we do, when you have some kind of label data, then you use LDA, that means your linear discriminant analysis. And when you don't have the label data, that means you need some kind of unsupervised dimension reduction method. That's the period when we do use the PCA, right? And then also, as I said that the PCA versus k-means is a quite important factor, because k-means is, it clusters points by minimizing the distance to the k centroid. We have seen that before actually. You pick a k, the algorithm assigns each point to its nearest center, recompute the center and repeats the process. We have seen it yesterday, right? So why you need to use PCA before k? Because when we do use together, we first need PCA, then we use k-means. So because the raw features can be noisy and correlated, right? That's the reason we kind of use PCA to compress them into a very few uncorrelated axes that keep most of the variance. And then we run the k-means in that PCA space usually, which gives us very cleaner, more stable cluster. And then we also speed the training in that way, right? And that's the reason we kind of do that. So generally how PCA works, if you will try to look into that, the center or the standardize the data, that's why first it does, and then it compute the covariance matrix, and then its eigenvalues or eigenvectors, okay? And once the eigenvector or eigenvalues are computed, then these vectors are the principal components, that means they are orthogonal in direction, and eigenvalues tell you how much variance each can capture, okay? So now you can see that the importance of the PCA compared to the other one. Basically PCA reduces the noise, PCA reduces the correlation, whereas k-means group the denoise patterns as strong baseline for the unsupervised SHM and many other tasks. So that's the reason we kind of try to use PCA and k-means together. First use PCA to reduce the noise, to reduce the correlation, and we kind of use the k-means to get a more stable data, right? And now if you will try to look into that how PCA works, if you imagine all features they are plotted in a multi-dimensional cloud points, PCA finds the axis of the maximum of speed of that cloud. So the amount of speed along each of the axis is the eigenvalue. So now if you try to first look into this particular figure here, okay, and then you come back here. So now if you will try to look into that, there are mainly two components which have been calculated in PCA. The first principal component, which is PC1, and the second principal component, which is PC2, okay? And that we have tried to show in this graph. We will talk about this graph, we will come back. So let's first try to see what is first principal component. So first principal component we try to denote as PC1. That is the direction in the space along which the data points have the highest or most variance, okay? That's been called as an PC1. So it is the line that base represents the shape of the projected points. If you will look into the PC1, you can see there is a most number of points here, isn't it? That's been called as a PC1. And what is PC2? That means the second principal component. So we calculate the second principal component, which is PC2, in the same way we calculate as PC1. That means PC2 amounts for the next highest variance in the data set and must be uncorrelated with PC1. You can see this is how we put it. So that means that PC2 must be orthogonal, right? That is perpendicular to the PC1. That's how we draw it, right? And the relationship can also be expressed as the correlation between PC1 and PC2 equals to 0, right? So as before, each sample has the PC2 score. That means each of these original values has a PC2 loading. So now if you will see how to use this plot. So our PC1 and PC2, if you will look into, this is the x and y direction. We plot the PC1 where we have more numbers, right, the more variance. And at a 90 degree, we have drawn PC2. PC2 is basically the next highest variance as a data set, okay? And always remember that correlation between this one and this one will always have to be 0, right? So if you will try to look into this plot, it is a very great diagnostic. The clusters or trends often separate along these two axes. Unusual points may kind of indicate or some way outliers, or you can also create some kind of new regimes. So in SHM you will see that PC1 often reflects dominant operating effects like temperature, okay? Whereas PC2 can reveal the secondary modes like local structural changes that are valuable for anomaly detection. That's where in SHM this graph is important. So basically in PC1 is that you can see some kind of dominant operating effect because you are getting most number of variance here, right? Where in PC2 most of the cases shows the secondary mode because it is having the second point where you get the most second or next highest and this mainly kind of talk about the local structural changes. And that will help you to understand the local damages, local cracks and any kind of anomaly, those are there. So from this graph you can see that PC1 explains the most variance, PC2 explains the most of what's left after PC1, right? And the two are uncorrelated, absolutely, and they gives a very clean 2D view of how the data's main structure could possibly look like. And that's the reason we kind of draw this, okay? Now if you will try to look into that how this PCA, and as I said PCA is nothing but principal component analysis, right? So most of the places we will try to define it as PCA. That's been applied in SHM. So there are few points, the few components, how do we do that? First what we do, we standardize the data, right? And that's what we have written, standardize the range of continuous initial variables. And how do we standardize the data? So the first step is that we standardize the range of continuous variables, okay? And PCA can be biased if some variables have much larger numerical ranges than others. We have to be careful that to fix that, we subtract the mean from each of these variables, okay, and divide by its standard deviation. Because it can have some kind of bias if there are some kind of larger numerical ranges. So what we do is that we subtract the mean from each of the variable and divide it by its standard deviation, and that's how we take care of it, right? So every variable has a mean of 0, right, and a standard deviation of 1, and that's how we kind of take care of it, right? And this will ensure that all features contribute equally to the analysis, right? The another one is that we compute the covariance matrix. How we do that? Once the data is standardized, right, we compute the covariance matrix. The matrix captures how variable can vary altogether, the variable can vary together. In other words, you can say that the correlation between each of the pair of variables, okay? It's symmetric definitely, with dimensions equal to the number of variables are required or squared. And this step is very, very important because PCA finds direction of maximum variance in the data based on the matrix. That's the reason we have to compute the covariance matrix when we talk about calculating or understanding the PCA. So then basically we first normalize the data to the same scale, that's what we do, and then we calculate the covariance matrix to uncover the relationship between the variables, right? And these are the foundations for identifying the principal components, which we will see here. So now we already covered the standardization, right? We have done the covariance matrix. So what the next? Now we will see that how PCA extract the useful information from the covariance matrix we just now generated, right? So for what, as I said that if we go back in we have done the covariance matrix, so that's what the same thing we have written here. So then what we do is that we compute the eigenvectors and we compute the eigenvalues of the covariance matrix, okay? So we calculate the eigenvalue, we calculate the eigenvector. So eigenvectors give the direction of the maximum variances. That means this becomes our principal components, whereas eigenvalues tell us how much variance each of this principal component can capture. That's the reason we kind of calculate eigenvalue, we can calculate eigenvector, correct? And by ranking the eigenvectors according to their eigenvalues, we can prioritize which components are important. Clear? So then once that is done, we have to select the principal component. And finally we decide how many components to keep. Components with low eigenvalues don't explain how much variance and can usually be discarded. And this is the way you can also reduce your data as well, right? So screen plots, that help us to visualize that. So the point where the curve forms as an elbow indicates an optimal cutoff, and that's how we generally do that. So basically you can understand that how PCA moves from correlation in the covariance matrix to find out, select the most meaningful direction where the principal component happens, right? Clear to everybody? And then after standardizing that, then we try to build up, transform the data into the new coordinate system, okay? So once finally the data is transformed into the new coordinate system, which is defined as a principal component. That is the finally vector which is being created from the eigenvectors of the covariance matrix, which we have calculated here, right? And then once that is being done, so once that you create the eigenvectors of the covariance matrix, the data onto the new axis define the principal components, which you can just see here, right? We just create the principal component, and this creates the new data which can capture most of the information, but with the fewer dimension. That means we are reducing the dimension than the original data sets, right? And then now there is a way that you kind of interpret the PCA results. So the PCA, if you go back here, similar way you also kind of draw this kind of graph after doing that, and then you kind of calculate where your variance lies, for PC1 and PC2, you kind of see that where your variance lies. You will see some of the points somewhere here, they are your outliers. That means you have to understand there are some kind of outliers, it does not actually stand over this, and then you kind of interpret the result. So basically PCA plot is a scatter plot which is created by using two principal components. As I said, PC1, first principal component, is the x-axis, and the second principal component, which is the y-axis. So basically this is going to be your x-axis and this is going to be your y-axis, right? And the scatter plot shows the relationship between the observation, that means the relationship between the points. You can see here. So this is generally how a PCA plot will look like, okay? And the new variables, which is the principal components. The position of each of these points shows the values of PC1 and the PC2 for the observation. That's how we generally do that. And the direction and the length of the point, plots and the arrow, they will indicate the loading variables, okay? And that is how each of the variable contributes to the principal component. Similar way, the number of the principal component that remains after applying PCA can also help us to understand or interpret the data output, okay? So basically, if you see that the PCA, they turns into the high dimensional structural health monitoring measurement into a compact de-noise representation, right? Isn't it? Because we are reducing the dimensionality some way, we are reducing the noise as well. So this is helping us in both of the case. And the plot, if you try to do the plot, you can see that you can actually get a relationship between the observations. So basically, the load explains which variable or sensor drive these patterns, and variance explain that how many pieces to keep. PC is nothing but principal component, okay? And then PCA is, as I said, is an unsupervised way to turn many possibly correlated features into a very few orthogonal principal components, right? Ordered how much variance they explain. So we try to keep the K components, as I said, and then how it is useful. So there are several ways, we can say, but I have tried to kind of write down the 4 important ones. So our vibration state, strain analysis, accelerometer data set, they are very high dimensional, right? They are very, very noisy. So that's the reason we kind of use PCA pre-process then to downstream the clusters or classifications, and then it becomes quite simple, it becomes quite robust. So the first one where we do use it is the image processing or image compression, sorry. So this PCA methods actually find a compact basis of images. They store a handful of principal components instead of all pixels, which reduce the size while keeping the visual details, right? And if you think about the SHM analogy, it actually compresses the thermo or IR images of the structure or a camera-based crack. If you kind of try to take a camera-based crack map, they're speeding up the storage and transmission without losing the exact critical damage location or exact critical damage details. Okay. Another place where the PCA can be used is that the data visualization. So basically, if you have project high dimensional features of 2D or 3D using the principal components to see the structure, that is cluster, trends or outliers. So if you think about plotting PC1 versus PC2, you can see that from the model features, you can see that you can actually calculate the healthy versus damaged set separately. Can't you, right? So that's where actually the data visualization helps us to understand how PCA works. And one of the very, very important one is that noise filtering, right? So high order principal components often capture sensor noise, right? And keeping only leading principal components can give a denoise signal. So that means when you have denoise acceleration or strain time series before the feature extraction or the frequency estimation, and that's what the PCA does, right? So standardized features first, that's what we do. Then we kind of choose a screen plot or cumulative explain here. So also you have to remember that PCA is linear. For non-linear structure, we don't use PCA. We use there's another way we do it. There is a kernel PCA we do use. There is TSNE. There is another one which is UMAP. So there are like several other ones we do use it for the non-linear cases. For the linear one, we do use PCA. Okay. So we will use PCA as a very front end up, like we compress, visualize, denoise or etc. That's the main three targets of PCA does when we talk about the SHM application, okay. So downstream the models, and also it kind of help us to run the model fast, it kind of help us to generalize the model better, right. And then another important thing which we need to see is that this is definitely a supervised one, and that is being called as an LDA. What is LDA? LDA is a linear discriminant analysis. So what is linear discriminant analysis? This is a supervised projection method. It looks like it looks at a level data. That means you need to have your level fixed compared to the PCA, and it finds the direction the best separate the class. Okay. So we use it when we need to distinguish two or more categories like healthy versus damaged using the feature vector. That's the time when we do use it. So LDA both reduces the dimensionality like PCA and maximize the class separately. Okay. So basically reducing the dimensionality and maximizing the class separability is the one what LDA does. It seeks a low dimensional subspace where between the class variance is a large relative to the within the class variance. Right? So that makes the downstream classifier very, very simpler and often more accurate. Okay. So what generally LDA does is that it maximizes between the class scatter while minimizing within the class scatter. Then the project data into the space and classify there. Right? That's where generally the LDA does. So then there are several assumptions also we do take in LDA, like LDA assumes approximately Gaussian class within the class equal correlance. But if you try to understand the main context of the SHM, you will see that we extract the feature. Feature can be anything, it can be modal or time frequency feature, and then we apply this LDA method to separate healthy and multiple damaged states. So if you have like 1 to 3 different type of damaged states, then you can actually separate it with the healthy to the damaged states. So if you kind of, now I kind of have something which I can do with data. So if you have something like this, right, and you have like 3 holes, this damage 1, damage 2 and damage 3. So this kind of methods will actually very, very good to kind of separate you with the healthy versus separate several damage states. Okay. So when I'm talking about just one rectangular structure here, you may have many. So you have like different damage state at different locations. This is a very, very good way where LDA is used. But you have to remember that this is a very supervised method. You have to really identify healthy and damaged state very, very clearly. If you do not label the data, you do not be able to use this one, right? So that's the easiest way. that you actually kind of calculate multiple multiple details or multiple categories using the LDA. That's the best feature about LDA. And now, if you will try to quickly, look into the summary here today. So we have actually tried to talk about a little bit about dimensionality reduction, right? Where we talked about PCA transformation, and we have talked about correlated data sets here. We are also talking about pre-processing steps like how we can standardize the data, we can calculate the covariance, derive the eigenvector, eigenvalue. And also we have looked into their key benefits like removing the redundancy, improve the computational efficiency, we reduce the overfitting as well. And with that we have also looked into where it could possibly be applied, like signal processing, damage, noise, visualization. Those are the places we have seen that how we can use the PCA. And then with the PCA we have also, so this is not been mentioned here, we have also used the LDA here to understand that when we have some kind of multiple damages or multiple states to identify, that's the period we kind of try to use the LDA as well. So now, as we said that we will always run out of the time, and there are a lot of details we need to always consider. There's a lot of future studies, a lot of current studies are happening which we cannot include due to the time constraint or syllabus constraint and other constraint. But I always keep kind of letting you know that this is something is very, very important, and you should definitely go and study along this. So the first one is definitely try to look into the multiple imputation with Bayesian models, because Bayesian models is kind of being used a lot. We have talked about MICE, but beyond that, if you kind of try to talk about multiple imputation at the same time, then try to use the Bayesian model for complex data sets, because we are nowadays always worried about big data sets, complex data sets. So please go and have a look into that. And then, as I said, that the learn about the probabilistic graphical models for missing data, like hidden Markov models or variational interface. That's the another important factor, that we have talked about the missing data, how we can generate those missing data. But how about if you kind of talk about the probabilistic graphical models? Like there are certain models we do use it. Go and try to have a look into that as well. And then another important factor is that realistic data imputation. We have not talked about the GIANs, which are also being used quite a lot in nowadays. That is like generative adversarial network. So that's been used quite a lot in SHM and many other cases. So again, my suggestion is that go back and have a look into that and try to understand how these models are, what they are actually adding on after what we have discussed. We have discussed the simplest one, we have then discussed the complicated one, or the case variance. But now if you kind of read these 3 points, how they are going to add on, and what could be the perspective or the situation when you need to use these 3 cases, right? And you will see that most of these are talking about getting a better data, or making your monitoring very, very sustainable, but also understanding the realistic monitoring. That's very, very important. Our aim is not to just reduce the data or dimension and get some random values. We have to understand the realistic monitoring, and we have to understand what data we have. But with that, if we can actually add on some extra things, that's always an extra add-on, right? So I will say that please go and have a look into that and try to understand how it actually works out. And with that, I will say this is the difference, as I said, that this is everything, whatever we have discussed today, is everything you will be finding here. And I will share, I think I will share a list of all of this with you soon after the lectures are over. And then also I have add on few of the other details which you may need to go through if you are interested to look into that. So with that, we will end the class today, and then I will take few questions from everybody. Yeah, let's take some questions from here. Yes. Sorry, I can't hear you. Yeah, so PCA will, if you see that most of the cases your data are not always labeled, right? So that's the period, you need your PCA. So it's like never like it's going to outperform. It's always like what information you have. So definitely LDA will be easier to perform, right? Because, and also the best part is that you get some multiple, like this I'm saying, like that's very, very common in all the structural cases, that you will have like lot of multiple damages in the bridges and different kind of damages, right? Those are very, very helpful if you kind of already give an, okay fine, this is how a damage state look like, this is how a crack look like, a fatigue look like, corrosion look like, or an healthy structure look like. So definitely LDA has much more benefit compared to PCA, but you have to also understand that PCA, so you have to consider that what you are looking for. But if you don't have, even if you have a damage, but you don't know how the damage will look like, right? You may not have the pictures of how the damage will look like, because maybe the damage happened in such a place where you could not go and take the photos. That's the place definitely PCA will work out, right? So it depends on what situations you are having, what data you are having, and how you are going to process or analyze it. It never like it's going to outperform. Sometimes you kind of take it together, and sometimes you have to select which one is better for your analysis.
And even told that for non-linear cases, we use PSA for those things instead of PCA, because
Yeah.
PCA is for linear.
No, PCA, yeah.
But my question is why, maybe there are many some export,
Yeah.
why we don't use the auto encoders?
No, so there are a lot of ways we can use that. So I have just given you 2 and 3 options. So we can use a lot, because we generally don't kind of deal with the non-linear cases most of the time. We kind of try to use either probabilistic case or the linear case. Non-probabilistic or non-linear, most of the cases we try to avoid. So there are ways we can do that. But what I try to say is that PCA cannot deal with any kind of non-linear cases. So I just showed like 2-3 examples. There are many other ways you can do that.
Other than SHM, example of phase recognition.
Sorry, other than SHM?
Other than SHM, take example of phase recognition.
Other than SHM?
Phase recognition.
Am I the only one who speaks very loud? I cannot hear you, I don't know.
Face recognition.
Yeah.
So in that process, they use PCA first, but after that we have to use LDA. So why not use LDA directly?
Yeah, see, for the face recognition also, if you kind of literally put the data, right, that this is how, it's all about labeling it. If you give the label information, you can use LDA, doesn't matter. But if you don't give the label information, then you have to use PCA, right? That's the basic difference between PCA and LDA. One is unsupervised, one is supervised. That means what? One we give the information, that label data, one we don't give the information. So you can use for any particular application depending on what you are feeding there. Anyone has any further questions? You were asking something, sorry, because I just wanted to finish it up because there were many things to finish. You were asking something.
I got the answer in the substance, like I was about to ask you what the data where we are trying to incorporate the missing data, like linking or more. When we are trying to do that for one value is okay, it is multiple values and
Yeah, that's the reason I have talked about the other ones where you can use it. Yeah. But you start with the main one, and then you can use bivariative, covariative, whatever the other options are depending on the case.
There was another question. In some slides, there was one line that was written below the PCA, that after getting the PC1, PC2 different principal components, we see the elbow, or from that we get the most informative
Yeah.
components.
Yeah.
So isn't it similar to k-nearest algorithm, because there also we get the elbow and
Yeah, some is similar, but k-nearest is more like identifying the neighbor, how that is actually values, and then replacing that, right? That's where we generally use it. And this is a different way to do that. But yeah, definitely it has some kind of correlation. But the whole purpose and the way it works is too different.
k-nearest for clusters.
Yeah.
Clusters. We have already identified the different principal components.
Yeah, but PCA is not talking about the neighbor values. It's talking about how the elbows will look like. That's a different. But KNN is talking about that taking the neighbor values, and then when you talk about the missing imputation, you replace that and all. But yeah, it does have a similar way. But then it kind of works in a very different perspective. Let's see if anyone has any further questions in the online. Okay, yeah, somebody actually answered when we were discussing about the sequential one, but I think that's the reason why you have to kind of see what they are talking about. Yeah, I think, so will they be able to hear me? So yeah, I think Manish, yeah, I think you have said the correct thing. That's what we were trying to discuss in the lecture. So basically, definitely sequential is much more reliable when we talk about the unstructured one. So that I think that's a good answer. Sorry, we couldn't see the chat that time. But I think we will be like more careful about monitoring the online people from now. But doesn't even have any further questions regarding this. I hope you all do have my email ID because I think Saturday is the last class, and after that Professor Shamim is going to continue with this. And then I will also give some questions and answers for the final one. But if you do have, and then I'm flying back to London only, so I will not be available. But if you want to reach out to me, I think you must have my email ID, or Professor Shamim will share my email ID. And I'm talking about for the online audience as well. So you can reach out to me if you do have any further queries or anything you want to talk about, right? So if not, then I think today we will end the class here. And thank you everyone for joining, and I will see you in the next one. Yeah. They don't have any questions.